Okay, hello everyone. Welcome to join our stream. We're gonna have the paper podcast in SIGMOD and the PODS 2025. And let me give you what happens in the next few days, this week. Today, we're gonna have the first talk. MAST towards efficient analytical query processing on point cloud data. Then tomorrow, we're gonna have the talk topic is duplicating the myth of joint order towards robust secure analytical cloud data. The talk will be given by the Zhang Huancheng from Tsinghua University, a professor. Also, the next. On the Wednesday, we're gonna have the talk named Architecturing the Next Generation Data System for LLM area. The talk will be given by two excellent PhD students from Southern University of Science and Technology in China. The student's name is Deng Yangsheng and Liu Haotian. Yeah, and the day after that, we're gonna have the talk on June 26th. The title is the Infrastructure as a Service Concepts of Data for LLM. And the talk will be given by Professor Zhou Xuanhe from Shanghai Jiaotong University, China. He's also the Jimmy Gray nomination award in SIGMOD 2025. And in the last day, the Friday, we're gonna have the talk titled is Low Latency Transaction Scheduling by the User Space Interrupts, Why Wait or Yet, and when you can permit. This actually is the SIGMOD's best research paper, and the talk will be given by Huang Kaizong from Canada University of Calgary. Let's back to today's talk. We are such honored to have the talk given by Jiang Li. Jiang Li is a current PhD candidate at the School of Computer Science and Computer and Data Science, Nanyang Technology University. Has research focused on database system, especially three-point clouds and multi-data analysis, as well as the interdisciplinary field like AI plus DB. And during his PhD study, has published multiple papers in top-tier conference like VRDB and SIGMOD. He also participates in several research projects related to anonymous driving and larger scale data processing. And today has a topic is I will let him introduce by himself. Again, in this whole week, every day, our talk will be studied at the same time, the 10 o'clock in the morning time, which means it's 4 o'clock in the afternoon, Beijing time. So don't miss the other days. The coming other days is excellent talk. So, okay, let's we welcome our first talk, the speaker, Dr. Li Jiangneng. Thank you.
All right, thank you very much. Thanks for inviting me to do this talk. Thank you, Fawn, and it's very honored to have this chance to do this presentation. And so today is the first talk, and there comes with a lot of famous professors and excellent works coming next few days. So I'm just a starter. So let's start my presentation. So this is the paper published in this year's SIGMOD paper called MAST on efficient point cloud data and analytical query processing. So first, let me introduce the outline. So first I will briefly introduce the point cloud data, its feature and its main applications. And then we started to talk about our motivation, why should we do this work? And then we introduce our main framework of our methodology. And finally, I will show some interesting experimental results. So first, let me talk about what is a point cloud data format. So a point cloud data is a new kind, is actually not new. So it's kind of sensor data by some laser or LiDAR sensors. So a point cloud data is, one point cloud is defined as a set of 3D points. So each point can have some actual features such as light intensity or RGB, for example, the color feature. So here is an example of the one point cloud frame generated by a smart car or smart vehicle. So this is a bird view image, and the white dots are the points. So the whole points combined is one point cloud frame generated by one time slot. So here, the application of the point cloud data before the autonomous driving and the VR scenario become famous is mainly used to generate some high definition maps for geospatial applications. But now, with the population of the autonomous driving and the VR scenario, it starts to do the main task for detecting the objects in the surrounding and interpreting the environment of the vehicle or other smart objects like robots. Right, so in this paper, we mainly focus on the autonomous driving scenario. All right, so during the object detection for the point cloud frames, usually we will include a lot of one deep model or multiple deep models to do such works. So one deep model will take a frame of point cloud as the input and output the bounding boxes of all detected objects. So here is an example, a smaller one of the same image. And you can see that the bounding boxes in the green or blue colors are the detection results come from one point cloud frames from the deep model, and the green one is the vehicles, and the blue one are the pedestrians. So very similar to the video and other multimodal modality data. So understanding the point cloud data will include deep models. So if we want to do some analytical job, so what we want to do is that we would like to reduce the usage of the deep models. So say we want to do some analytical including the spatial predicates. So what we say is that we want to get the amount or the count of the cars that within a spatial range that we presented as a red circle in here. So we want to retrieve all the satisfied PC frames that with less than 3 vehicles within the red circle. So this is a very typical spatial predicates that can be used to analyze the PC frames. And if we use the deep model to process all the PC frames, it will be very costly. So the bottleneck of doing such analysis is that we need to include the deep model to do all the processing. So our motivation is that if we can reduce the usage of the deep model. So here comes our targeted queries. So we target like 2 main query types. The first one is the retrieval query, and the second one is the aggregate query. So for retrieval query, we have 2 main predicates. The first one is the spatial predicate. So we would like to have a spatial range that restrict all the objects inside, and then the semantic predicate. We call the semantic predicate on the number of the objects. So we want to restrict that how many objects are within the spatial range. And then we also want to, during the analyzing of such kind of data, for one application is that we want to analyze the people's driving habit. So if they are doing dangerous driving during their driving period or not, so we would like to see if they are driving too close to the other cars. So in this case, we would like to aggregate like what is the average car number within 1 meter of the car that is driven by the driver, and if the car number is very high, which means the driver intend to drive very closely to the other cars, which will result in very high risk to the car accident. Right, so this is the real application of the aggregate query. So in this paper, we consider the input data as the point count sequence. So which means that the point count frames are generated with a static frequency. Say we have the FPS of 10, which means that 10 point count frames are generated within 1 second. All right, so here comes the question: how to facilitate the leverage of deep model during conducting such kind of queries? So this is our framework of MAST. It's mainly consisted with 3 modules. The first one is the sampling module, which samples the key point count frames. And the second one is the spatial temporal point count analysis module, which will analyze all the PC frames with the spatial temporal continuity features. And the last one is the query processing module. All right, so our solution to reduce the usage of deep model is to doing the sampling. So we only sample the important point count frames to be processed by the deep model. So and then we will use the result of the processed PC frames to predict the spatial mobility of the other unsampled frames. So the second question is that how can we detect important PC frames? Right, so here comes the spatial temporal continuity analysis module. All right, so we want to make use of the real world settings. So in the real world, in the physical world, that the objects are not like instantly from one position to another position. Right, it's actually moving smoothly from one position to another position. So if we say we have sampled 2 point count frames, one in the time slot T1 and another in the time slot T2, so this is how the deep model predicted the situation of the objects. So in the figure 1, we have 3 cars, car 1, car 2, and car 3 in different positions. And then when we use the deep model to predict the second frame, we got 4 different cars: car 1, car 2, car 3, and car 4. So in here, the deep model predicting the frames, they have totally, they'll simply predict 1 frames and get the object information out from 1 frame. And then we do in this modular is that we align the objects predicted by these 2 frames, and we say that, okay, we're doing the match, and after we're matching, we found out, okay, these 2 cars are the identical cars, and they are moving from the position in the PC frame 1 to the position of PC frame 2, and here we are predicting we have a velocity of different cars. And also we have the car 4 as the new appeared cars. All right, so now we have the predicted mobility situation from PC frame T1 to PC frame T2, and now we are predicting that what is the situation in the PC frame in T when T within the interval from T1 to T2. Right, so so this is a quite simple spatial temporal model. So we assume that the cars are moving with a static velocity, and then the cars will moving in the middle side of the start point and the end point. So in this point, this is our predicted mobility situation of this frame. All right, so in here, so if we have 2 sampled frames, then we can use the modular to predict out of the mobility situation of the frame between these two frames. All right, so this is the spatial temporal modular. And then we use the reinforcement learning model to guiding our sampling. So first, we are doing some uniformly sampling out from the PC frame sequence. So as we can see that we sparsely and uniformly sample some PC frames, and those PC frames will segment or split the whole point cloud sequence, segment BU minus 1. So the BU means the budget of the uniform sampling. And then we initialize one RL agent in each segment, which is first we have an agent that is initialized in the root node, which will guide to decide which segment to be selected. And then so here is a small sample. So currently we have done some sampling already. So here comes a new sample. So from the root node, we have the pi as the policy. So we have initialized the reward or the value of each. The algorithm tells us, okay, we need to select the segment 1 as the choice. And then another agent, which is initialized in the segment 1, which is pi 1, will then apply another UCB algorithm to select the segment 2, segment 1, 2 as the second subsegment. After 8, we will select the middle side of the subsegment S1, 2 as the output frame, as the sample frame. And afterwards, the output of the sample frame, afterwards, we have sampled one frame, and then we generate the reward. So we designed the reward to evaluate how important is this point cloud frame. So basically, our idea is that if the sample frame, after we process it with the deep model, and we can get what we call ground truth mobility situation. And then we compare it with the spatial temporal predicted one. So we compare how different it is to say if these two are very similar, which means that with the current sampled PC frames, we can already predict the mobility situation of this frame very accurate, because the spatial temporal predict one the predicted result is very similar to the ground truth. And if it is very different, which means that it is very important, because the current sampled frames cannot predict the mobility situation very accurately. Right, so then we will design a very large value that shows that this PC frame is very important. We have actually sampled the accurate frame to make our query performance more accurate, our query more accurate, right? So after we have the reward, we will update all the related agents, say the pi1 and pi, and update the value of the R1 and R12 to show, like, okay, so with the current sampling, how good it is. So if it is good, then the reward will be increased, right? And afterwards, with the new frame sampled, we will further segment it into smaller segments. Okay, and then we will initialize a new agent to the S12. So basically, this is a multi-agent framework, and basically we are applying, assigning different agents to different segments, and with one sampling the pace from the root to the real sampled segments, say S12, all the nodes on the path, the agents will be updated with their values. Okay, so this is the main idea of this this method, and here comes with some experimental results. All right, so basically, before we go into the experiments, so we say that the sampling, when you're doing some unstructured data analysis, is actually quite normal. So everyone wants to do the sampling, but how you do the sample is different. So everyone has their own opinions. So in our opinion, we are using the physical world to help us, to guiding us to do the sample. So basically, if we can predict a sample very accurately with the current sampling, then we do, with the majority situation, we do not need to sample it again. So this is our high-level idea. Right, so here comes with the experimental results. So we have evaluated our method on multiple data sets. So 2 real data sets, the semantic kitty, and the once. So the once data set is actually released by Huawei. Right, so it is named the 1 million LiDAR scene dataset. And the scene, another scene LiDAR is a synthetic dataset. We actually use it to evaluate the scalability of our method. Right, so in here we can see that MAST has outperformed the baselines. Actually, the Staden baseline is the a baseline that we adapted from the video community, video analysis community. He's doing the sampling on the video images. And the Staden PCSD is that the baseline with our spatial temporal analysis module. All right, so we see that master actually outperforms all the baselines on majority of the PC sequences. And this is the aggregate query. We actually evaluate multiple aggregate operators, including the count operator, and average operator and median operator. So we can see still our method has outperformed the baselines in different degrees. All right, so actually, oh wait, so why this picture does not occur? Okay, so here is some. So all right, so in this picture, actually we are trying to evaluate what kind of sampling is actually preferred to make the query results better. All right, so our insight, we have done some experiments. Okay, so but the figure here does not appear accurately. So, but you can check it in the paper actually. So our result shows that the sampling result of MAST has actually capturing the local minima and the local maxima of the number function. So as we can see, if there is a function that showing the change of the car number within one spatial circle, let's see, and it is changing, and if the sampling are sample accurately on the local minima and the local maxima, then we can mimic the number function very accurately. And then as a result, we can have an accurate query result because we are generating the approximate query results based on the function that we predicted. Right, so I think that's very much of the presentation. So this is for the slides is for the conference paper, so it's relatively short, I think. So let me know if you have any questions, right? Whether offline or online. Okay. All right, thank you very much.
Okay. It's a very nice talk, and actually, I got one question. What's your plan about the 18 plan about the future of work continue this autonomously driving direction topic?
All right, so in this work, we are mainly focused on the point cloud analysis task. But actually, for the autonomous driving, usually is not single modality tasks. All right, so for those kind of tasks, so usually they have multi-modalities. So including the point cloud data, including the video data, and sometimes with the audio data of the driver. So usually the car will also record in the audio that to see what's happening within the car. Okay, so our next task is trying to do some analysis on the multimodality data. So still, which means that this will result in more general usage of the applications. And there are a lot of like interesting questions that can be done, like the data retention, like what kind of data modality is most useful for a task, and we need to retain it in the database storage. And also like during the analysis, which kind of modality should be used and which kind of modality does not need to be used. And there are a lot of interesting research questions that can be searched. Right, so, and we are also including some new scenarios, like currently we are doing some works that is with only one point cloud sequence, and we are doing some current work that is including like multiple point cloud sequences, like multiple vehicles, like we jointly analyze those vehicles and to get a more accurate query result, right?
Okay, thank you. And if for the audience online, and if you have any question, can send the messenger on the chatting box, and our staff will collect the question and give the question to the speaker, and we will let the speaker to answer the question later. By the email or by the WeChat, because I got the WeChat has in WeChat information. So we are welcome to for the audience online to have a closed connection or communication with the speaker.
Yes,
thank you so much.
All right, thank you. You got a question?
Also I have a question. Yeah, sorry.
All right.
I'm quite curious about the reinforcement learning part, and yes. I think the idea is very good, and so I'm wondering, so how to design the verify, because verify, so I think the verification is very important. So could you explain more on the verify for this reinforcement learning part?
Verify?
Yeah, verify.
Oh, sorry.
So because if you reward is generated by the verify and the outcome. Right. So
yes.
So I would like to know the detail of the verify part.
Yeah. So the reward design is the most important part of the reinforcement learning, of course. So basically, it's just among your aim. So your ultimate goal, like what the reward is reflecting. So basically, in our framework here, we want to reflect that if the outcome of the frame or the PC frame is very different from what we are predicting with the current sample PC frames. So basically, after we sample one point cloud frame, we'll process it with the deep model. So because that we have already decided to sample this point cloud frame, right? And then it will be processed by the deep model, and there is no extra cost. And then we will get the predicting result with the bounding boxes, right? And then we will use the spatial temporal analysis modular. So we will collect the most nearest point cloud frames that are sampled already, one from the left and one from the right. And we will use what we just introduced, the spatial temporal analysis, to get the predicted result. And then we will analyze the difference between the predicted result and the deep model predicted result. Right, and we will use it because we are using the Euclidean space, so we will calculate the Euclidean difference between the predicted bounding box and the evaluated bounding boxes. And then we will average the distance, and which will be the final reward. But actually the real reward is more complicated, but you can just understand in that way, right? So if those two predicted results are very similar, then the reward will be very small. And if they are very different, say one object is in this side and but the actual object is in the other side, then the reward will be very huge because we cannot predict it very accurately currently, right? So that's how the reward is generated.
So thank you very much. Yeah.
All right. So, all right.
Okay. Thank you for talk. I think from your team, there are more papers on this SIGMOD. So besides this paper, do you have any recommendation that we on-site or offline audience can have follow-up later?
Sorry, what?
Other papers from you or your team on this SIGMOD this year.
So you mean, is there any other paper?
Yes, you recommend we can follow up.
Of course. So we got our SIGMOD paper in this point cloud scenario, and we also got the demo of this framework. So in Thursday afternoon. So for this, we do not got the oral chance, but we have our poster session in tomorrow. And we also have our team, one is in the vector search. So vector plus vector search called DG, and also published in this year's SIGMOD. And we also have our BT tree is a binary tree, is a learn index. As we see, is a learn binary tree, right? For trajectory indexing, I think, right? And we also got a LSM tree based work, but the one who he did not manage to come to Berlin, so Professor Chong will present it for him, right?
Okay, thank you. And for this work, do you have any follow-up ideas or research later on, or that's it?
Yeah, actually, we have submitted one paper on the storage optimization of the point cloud data to the very large database conference, but it just got rejected. So we will recycle it into next year's SIGMOD, I think. And we also got some one or two more projects which is still undergoing, right? So it's not finished yet. So I think, yeah, more works will come, right?
Okay, thank you.
All right. So.
Okay, thanks again, Dr. Lee. Have a so nice talk. Thank you. And again, this week, from the same time, we have a very nice talk. Each talk is related to the excellence paper published in SIGMOD PODS this year, 2025. And the time is Beijing time, afternoon, 4 o'clock in the afternoon. And the boarding time is 10 o'clock in the morning. So welcome to back tomorrow. And of course, in the future few days, welcome back to here again. So, but today, I think that's all. Thank you much. Yeah. Yeah, see you tomorrow, the same time.